Okay, we are recording. So first things first, exam 2 has been graded. The grades have been released on Gradescope. An email has been sent with the statistics on exam 2, and the distribution is over here. As you can see, there are only about 7 people above 80. So in my opinion, if you are above an 80, you did extremely good on this exam. So 83 was, I think, the 3rd highest or the 4th highest in the class. So, when you look at your exam score, you have to also sort of put this chart, right? Like you don't treat your scores as absolute numbers. Look at it in as a relative number to the rest of the class, because at the end of the semester, I do this. I try to put people in clusters, groups, right? I don't curve anything, but when I look at, say, my best group of students, where is it? If that group happens to be between, say, 85 and 90, then 85 is going to be my cutoff for an A, right? So that's how sort of I do my curving. I hope that makes sense. And I go for clusters of students in which I can clearly separate out those grade lines. Because if somebody is missing some number by, say, 0.3%, they don't deserve a different grade, right? So I go for some separation. Sometimes, most times it is possible. Sometimes it's not possible, so I try to do the best over there as much as I can. Okay, so above an 80 superstars, you guys rocked it for exam. But even if you are above a 70, you did very well. So, there is a lot of good things that came out of the exam. I looked at some of the solutions, and they were very, very elegant solutions. So good positives, but there's a lot to be concerned about as well. So if you are sort of a below 30 mark, I think you're in a danger zone. So we got to figure out something. If you are continuing with the class, we need a good strategy for the final exam. This is not going to cut it, right? Signals and systems is the pinnacle of your undergrad education. If you are EE or CSE, that's like top of the mountain. So if you're not doing well in this course, then your whole major is sort of in jeopardy. So Fourier transform and Fourier series, if you say I'm an electrical engineer and apply for a job, if you're not really solid in Fourier series and Fourier transform, which were the contents for this exam, then it's not going to go well for that particular conversation or interview. So we still have a few topics that are coming our way. We have Laplace, feedback, Z transform coming our way, right? Which are also very relevant, very important topics. But FS and FT are the first ones that come to mind, right? Those are right in the center of the course. Let's see. So if you are below a 30 mark, then as usual, I would very strongly recommend you to have a one-on-one meeting with me. Preferably this week. Don't leave things late. We only have about 3 weeks, or 3 weeks, just over 2 weeks left in the semester. 3 weeks, all right, 3 weeks left in the semester. So almost a Gaussian distribution, this one. Okay, highest was a 91, only 2 scores above a 90. Average and median and mean were pretty close to each other, 54 and 54.5. Standard deviation pretty high, 20 points. All right, questions, concerns? Yes, by email, right? So regrade requests within a week by email to me. But those are your grades. All right. Is it too late to? All right, I'm not going to repeat that question. here, everybody has a difficult exam, right? Like everybody gets an exam where they don't do really well, and that has definitely happened to me. In fact, my first exam in the US, I think I scored a 44%. So that was not a good start, but I got an A in that class because I worked really hard, and I proved to the instructor that I was good at DSP. DSP was my home, and I can't get a 44% in my strong area. So I scored the best on the final. I scored a 95%, make it a compelling case to score an A, and I did. So everybody has a bad exam. The reasons could be, yeah, I was not able to do the math. There were silly errors. So if there were mathematical minor errors, I'm not worried about that at all. That can happen even in the solutions. If you dig deeper, you will find some there. What I'm worried about is more serious errors, right? Omega and t. You can either be in omega or you can be in t. Sometimes when you're asked Fourier transform and you're going to write something as a function of time, that's a pretty severe error. So those are the things that I'm worried about. So the instructions to the TAs were to penalize those severe errors more than the mathematical ones. Okay, I think this is it for the discussion about the grades. We can move on to Laplace. Okay, so we are talking about properties of Laplace transform. Excuse me, we talked about the linearity property. We did an example. The next property that we are, just to remind you, linearity property. So if the Fourier transform of f1 of t is cap f1 of s, that is given, the Laplace transform of f2 of t is cap f2 of s, Laplace transform is given, both their regions of convergences are also given, then what you can do is, if you're scaling a, you have scalars a and b for f1 and f2, the Laplace transforms of each of those signals will also get scaled by the same scalars a and b. And what do you do about the region of convergence? Well, you find the intersection of the region of convergence. And we talked about why that is going to be the case, right? This guy has a pole here, region here. If this guy pole here, in region of convergence goes there. Wherever the regions of convergences intersect, that's going to be the place where the overall signal converges. So for an example, we did this. This will be a quick refresher about Laplace transform for standard signals. So the Laplace transform for impulse, constant. In this case, we are just multiplying by 2. U of t, 1 over s. T of t, 1 over s squared. And for each of them, what are we doing for the ROC? Well, for impulse, we know the region of convergence is going to be all of S plane, complex plane. For U of t is going to be a pole at 0, pole at origin, and then the region of convergence is going to be everything sigma greater than 0. So right of the pole. And similarly, for TU of t, it's going to be to the right of the poles. In this case, 2 poles, right? Both of them at 0, 1 over s squared. So that's 2 poles at origin. And then if you find the intersection of everything sigma greater than 0, sigma greater than 0, you get sigma greater than 0 as your region of convergence of the overall signal. Next, so this is new material. Now, what about time shift? When you time shift a signal, what happens to its Laplace transform? Proof not given here. Why? How can you prove this? Take the definition of Laplace transform, do the math. You will have to be doing a change of variable. T minus t0 is tau. Change of limits of the integration, blah, blah, blah. You guys know the deal with that. Exactly the same way as you prove the time shift property for Fourier transform. That's how you would prove it. So the properties that we will list for Laplace, we will not go into proofs. We will just state them, and then we will use them for examples. So if you say have a Laplace transform here for f of t Laplace transform is f of s, and you also need the region of convergence here. We have the region of convergence is, say, some region R. If you shift this time signal by t0, then you get a e to the minus st0 in the Laplace domain, exactly as we had in the Fourier domain, right? In the Fourier transform, you had e to the minus j omega t0. Now you have e to the minus st0, where t0 is your time shift multiplied by f of s. Region of convergence doesn't change. Why? Because now you're shifting the signal, right? Here and here. You're not doing anything to how the region is going to change. The region of convergence is going to change. It's going to have the same limits for sigma. Region of convergence doesn't change when you shift the signal in time. Now, using that, let's try to find out the Laplace transform of u to the u of t minus 2. So you have delayed the signal by 2 time units, a unit step. For u of t, we know u of 1 over s, right? So we can quickly write that down. For u of t, my standard pair that I'm going to use here is this. I can't even write down real part of s greater than 0, right? So I'll use that. So I've got this, real part of s is 0. Now, because of this time shift of 2 units, you will multiply by e to the minus 2s. Real part of s greater than 0. ROC doesn't change. Questions about this example? Now, with this, you should be able to do delta of t minus 2, right? In fact, you should also be able to do something like this. T minus 2 times u of t minus 2, right? Because we saw Laplace transform of 3 signals, delta, u of t, tu of t. For any of those signals, now you should be able to apply the time shift property and be able to get its Laplace transform, which includes both a function in S and the ROC. Next, let's take a look at an example over here. Here we have a finite duration signal. Earlier, delta of t, well, u of t was going on, right? T of t was going on. Now we have a finite duration signal. So it starts at 1 and ends at 4. And it has that particular shape. The question is, what is its Laplace transform? So what we can do over here is we can represent f of t as ramped functions. In other words, t u of t's. So you have t minus 1 times this. So you have one time window here, right? So this is one time window. My one time window is between 1 and 2. And to create that gate function, I have this, which is essentially g of t minus 1, right? And then I have another guy, and that is multiplied by a ramp. What is that? It's a line that has a slope of 1 and a y-intercept of how much? -1, right? So you got t minus 1 there. And then between 2 and 4, it is simply a gate. So open the gate at 2, close the gate at 4, you're done. With this, you can expand it out, distribute t minus 1. You got t minus 1 u of t minus 1, t minus 2 u of t minus 2, and then u of t minus 4 over there. You have just combined the common u of t minus 2s. Next, if you look at this guy, this is t u of t delayed by one time unit. For t u of t, I know it is 1 over s squared with real part of s greater than 0. When I delay it by one time unit, I get e to the minus s, right? So because of this guy, I have this. And because the function is t u of t, I have the 1 over s squared. And I'm doing a time shift, so the region of convergence doesn't change. It is going to be still region of convergence of s greater than 0. Similarly, I do it for the next piece. I have t minus 2, u of t minus 2. Because I'm delaying by 2, I get e to the minus 2s in the Laplace domain. And because the function is t u of t, I get 1 over s squared. Again, region of convergence is real part of s greater than 0. Last one here, which is simply u of t minus 4. For u of t, it is 1 over s. For u of t minus 4, it will be 1 over s, but it will have a e to the minus 4s in the Laplace domain. Region of s, go ahead. Yeah, so that's my note here. You're going ahead, but okay, so it's not going to be, so if when you find the region of convergence by finding the intersection, that is at least, right? That's giving you at least this much, but you can have more than that, which is what happens over here. So if you find the intersection of all these region of convergences, it'll say that the region of S is greater than 0. But clearly, when you look at the signal, it is finite duration. Starts at one point, ends at one point. So it should be able to converge everywhere in the S-plane, which is what it is. Actually, it is all of S-plane because it's finite duration. However, when you apply this property of intersection, what you get is at least this much, right? So at least it is real part of S is greater than 0. In a couple of slides, we will look at a property where we will be able to say finite duration ROC has to be all of S-plane. So good catch there, yes. So we'll have a property. There's a mathematical proof as well, but we'll not do the proof to save time for other interesting things. Other questions? So given a sketch of a signal, are you able to find its Laplace transform, which includes both a function in S and its region of convergence? All right. Next, frequency shift. So time shift is run. Now we are shifting in S, right? So if there's a Laplace transform pair here, f of t, Laplace transform, f of s, region of convergence is R, then when you have a signal, when you shift in Laplace domain, f of s minus s0, then exactly like Fourier transform, you multiply with e to the s0t in the time domain to the function f of t. Now in this case, the region of convergence also gets shifted. You get a shifted version of the original region of convergence. Let's take a look at that with an example. Here you have a Laplace transform that you need to find for e to the minus 2t u of t. And we know the Laplace transform pair there. It is simply 1 over s plus 2. I think that was one of the first things that we did, right? E to the minus sigma or e to the minus at u of t. It is 1 over s plus a. In this case, a is 2. So we said e to the minus 2t u of t, it is going to be 1 over s plus 2, where the region of convergence is to the right of the pole because it's a right-sided signal. Real part of s is going to be greater than, where is the pole? At -2 on the real axis. So from earlier, what do you have? U of t shifted by u of t Laplace transform was 1 over s, region of convergence was real part of s greater than 0, right? That was for u of t. When you shifted in the Laplace domain, what do you have? Instead of 1 over s, you have 1 over s plus 2. You guys see that? So this is relating to the frequency shift property over there. So in the Laplace domain, you had a shift by 2, which means that in the time domain, you had a multiplication of by e to the minus 2t, just as the property says. But look at the region of convergence. Original one was real part of s is greater than 0. Now we have a shifted version of R, right? It was real part of s is greater than 0. That whole thing has shifted now by to -2, starting from -2. Can you see that? All right. Time reversal. What happens to the signal in Laplace domain when you shift the signal in the time domain about the vertical axis? F of t, f of s, a pair of for Laplace transform, region of convergence, R. When you go for f of minus t, you're flipping the signal about the vertical axis. You also flip the signal in the Laplace domain. And in the ROC, you get the flipped version of the original ROC. So if you look at this, right, what would be the flipped version of this guy? Well, it would simply be real part of s is less than -2, right? It would flip. So instead of being to the right of the pole, it would go to the left of the pole. The reason being, you are taking a right-sided signal and turning it into a left-sided signal. So the ROC also flips. All of these properties are summarized on the Laplace and Z transform tables that you can find on the resources on Piazza. All right, so let's see. Example about that. Let's try to find the Laplace transform of u of minus t. U of t, 1 over s, region of convergence, sigma greater than 0. U of minus t, minus 1 over s because of this property, and sigma is less than 0 here. So the region of convergence in the S-plane has flipped about the vertical axis, which is j omega axis. Questions here? Time reversal, frequency, time shift, frequency shift, time reversal. 3 more properties that we added. In terms of standard pairs, how many do you have? e to the at u of t, right? And then you also have e to the minus at u of minus t. Then you have t u of t, u of t, delta of t. Right? So far that's our set of standard Laplace transforms and some small set of properties as well. Next, we will take a look at time scaling. All of these properties are looking very similar to FT properties, right? Fourier transform of a signal is given f of s, region of convergence is given R. Now, if you have a time scaled version of f is at, the Laplace transform of that is going to be 1 over absolute of a, f of s divided by a. Exactly the same as you had for Fourier transform. What is the ROC going to be? Now, because you're changing the scale for s, your ROC is going to be scaled. R is now going to become AR. Let's try to take a look at an example. You have e to the minus t, 2t u of t. We are trying to find its Laplace transform. Let us start with e to the minus t u of t. If you start with e to the minus t u of t, I know that its Laplace transform is 1 over s plus 1, with the region of convergence being sigma greater than -1. Sigma is real part of s. We know that from an earlier thing that we proved. Right? We looked at s1 over s plus a, 1 over s minus a, and we considered two values of a, plus or minus 1. One of those in that table is this. Now let's look at the signal that we actually want. E to the minus t u of t can be written as e to the minus 2t u of t, 2t. You guys believe that? You guys agree with that? Can I write u of t as u of 2t? It's going to be the same signal, right? T less than 0, it's 0. T greater than or equal to 0, it is 0, 1, right? So no matter if you scale, this guy is going to be the same as this guy. So I can write that as a function, but instead of t, now I have 2t. So my a is 2 here. So I get what? In the Laplace domain, using the property, I get 1 over 2. And instead of s, I have s divided by 2 here. And now you can simplify this to get whatever. What are you going to get? You are going to get 1 divided by s plus 2, right? That's what you will get here. Because I know the property of this. It is going to be 1 divided by s plus a. In this case, a is 2. So I already know the answer is 1 divided by s plus 2. You should get that. How about the region of convergence? You should scale the region of convergence. Earlier, real part of s was greater than -1. Now, real part of s divided by 2 is going to be greater than -1, which means real part of s, sigma, is going to be greater than -2, which is consistent with our result for e to the minus a u of t. E to the minus at u of t. You guys remember that result? Let me just write that over here. At u of t Laplace 1 divided by s plus a, right? So there's a pole at -a. So this should be real part of s greater than -a. Yeah? So go ahead. Oh, it cannot be time flip, right? Because you are not flipping u of t. If you want time flip, then you have to, all t's should become negative t's. Because only then you become a left-sided from a right side. Yeah, from the, here. Oh, for here. Okay, yeah. No, it can be -1. Yeah, absolutely. So if it was -1, you would apply that along with this, right? Yeah. A can belong to any real number in this case. Now, as far as this property is concerned, it's a different A. So maybe I should change this, because this A can be complex, right? Let's see. I'll put B here and put B here, and all I would have to do is I'll have to change this to B, right? So They're different now. All right, let's see. Let's move on. Time scaling done. Now, what is important here? Is it difficult to is it difficult to compute the function in Laplace domain? No, it's not. But it is slightly confusing to look at the region of convergence that has been scaled or shifted or flipped, right? So hopefully these examples show you how that flipping happens, how that scaling of the region of convergence is happening. So this getting here is not that big of a deal. This is. All right, let's move on to properties, which is now derivative. We all love to derivate our functions, right? Quadratic to linear to constants to impulses. We love that. So let's try to see what happens when you differentiate in the Laplace domain or in the time domain. So when you take this particular form here, which is f of t, take the Laplace transform, you get f of s, region of convergence is R. When you differentiate the signal in, sorry, let's not do that. If you multiply the signal in time by t, you're actually differentiating the signal in Laplace domain along with the minus sign. Where have we seen this before play out? When we went from u of t to u of minus t, right? U of t, you got 1 over s. U of t, you got 1 over s squared. Both of them sigma greater than 0, right? So you see, when you multiplied in time by t, you actually differentiated this guy and multiplied by a negative sign, right? Minus 1 over s squared. I see it? Region of convergence didn't change. This guy was sigma greater than 0. This guy was also sigma greater than 0. Now, when you differentiate the signal in time domain, what would that be for? So let me just differentiate this guy in time domain. When you differentiate u of t, what do you get? An impulse in time domain. What is the Laplace transform of this guy? Just 1, right? We just multiplied f of s by s, right? 1 over s times s, you got a 1, right? What about the region of convergence? ROC. All of complex plane, right? But it is at least R. It is at least sigma greater than 0. But for this specific one, because we know the ROC for impulse, we can say it's all of ROC. So essentially, to just summarize these properties, when you differentiate the signal in time domain, you increase its region of convergence, right? You are increasing that linear of convergence because it's at least the original one. But when you differentiate in the Laplace domain, you don't change the region of convergence. Questions? Go ahead. Yes. And that is actually our next property, I think. No, we will get to the integrating property as well. But you're absolutely right. The powers of s or t will keep increasing. Let's see. Derivatives are done. Let's take a look at an example. So here, I usually work out this example in front of you in class, but I'm trying to save time here. So f of t. Again, I'm using the piecewise model. I have 2 lines, right? This guy is 1 line here, which passes through 0, goes up with a slope of 1. So that's just t. So I'm going to take this t and multiply it with this gate function here. Opens at 0, closes at 2. So I've got that, right? T times that gate function. And then for this guy, you see, in 1 time unit, it goes to 2, 6, 9, right? So this guy, sorry, here it is, at 2, it is at 2. At 1, it will be at 4. And then at 0, it will be at 6. So the slope is -2, and the y-intercept of that will work out to be +6. So you can write the equation of this line as -2 plus 6. You have to also multiply it with a gate function that opens at 2, closes at 3. So that's u of t minus 2 minus u of t minus 3. And now you have got a function f of t that has t's, u of t's, and all that, and you're trying to find its Laplace transform. So you could actually do this directly as well, but we'll try to do it with the derivative property. You could have done it directly as well, right? We know t u of t's. We could have done it directly as well. So let's say we want to use the derivative property. So if you differentiate it, what do you get for the first one? Well, t is slope of 1, so you multiply it by 1. The gate function is still the same, but instead of multiplying by t, now you're multiplying by 1. How about for the second one? Well, the slope is -2, so you're multiplying by -2 for the same gate function, right? You're just evaluating the slope of those lines for one gate function and the second gate function. When you differentiate this signal second time, u of t will become an impulse. U of t minus 2 will become an impulse over there. U of t minus 2 will also become an impulse over here. You have a -1 from there, -2 from there. Overall, it becomes -3. And then you have a -2 delta of t minus 3 plus 2 delta of t minus 3 from there, right? So you went from ramps to steps to impulses. Now let's try to go back. When you have differentiated the signal twice in the time domain, you essentially multiplied by the signal by s every time, right? So s squared f of s is the Laplace transform of this guy. For delta, you have got 1. For 3 delta of t minus 2, you have got 3 e to the minus 2s. For this guy, you have got 2 e to the minus 3s, right? Just using time shift property. If s squared f of s is this much, f just divide by s squared, you get function in the Laplace domain to be this guy. And going back, it's a finite duration signal, so I can say that the region of convergence is going to be all of S plane. Questions about this example? I could have gotten this result directly, right? I didn't need to use the derivative property, just as an example to show how it would work here. Questions? All right. Can somebody ask a question? Because I want Marit's question not to be the question that keeps looking at me. That is that right? I keep looking at the chat box and that question sort of just there staring at me. All right. Let's move on to the integration property. So if you have an integration in the time domain, earlier you were multiplying by s. Oh, there you go. We have got a question. Why is 2 delta of t minus 3? I think it's right here. 2 delta of t minus 3, right? This guy. So you see, if you look at this multiplied by this, what do you have? You have plus 2u of t minus 3. And you differentiate, you get this, right? And then, okay, so just to make sure, all of this and this is going here. And this guy is actually going here. And then the blue guy is coming here. Does that help answer the question? All right. Let's move on to the integration property. F of t, Laplace transform, f of s, when you have your integration, when you integrate the function in time from -infinity to some arbitrary time t, you will be dividing the function by s. So let me ask you guys, what do you think happens to the region of convergence? Does it become smaller? Does it become bigger? Try to think of it in terms of an example, right? So let's try to see if you have u of t, you have got 1 over s squared, 1 over s, and then you have real part of s greater than 0, right? And then when you differentiated it, you had this. all of S-plane. So when you integrate it, you went from here to here, right? You had more constraints, right? So ROC actually becomes smaller as you go. So what can you say? At max, it is going to be the original one, right? Earlier you said at least the original one. Now you can say at the maximum, it's going to be the original one. Next, existence of Laplace transform. Actually, when we were looking at the motivation of the Laplace transform, we talked about this. This is a more formal look at the same thing. When does the Laplace transform exist? In other words, why are we talking about ROC only in terms of real part of S, only in terms of sigma, right? This is the proof for that. Laplace transform of f of t exists if the signal is absolutely integrable, and also it should also be square integrable. Absolute integrable is what? For what? F of t along with that borrowed factor of e to the minus st. So if this has to be absolutely integrable, you can actually break this e to the minus st down into these two factors, e to the minus sigma t, e to the minus j omega t. Try to find the magnitude of them. E to the minus j omega t doesn't give you a magnitude other than 1, that is unit magnitude. The actual signal that you are looking for it to be absolutely integrable is f of t e to the minus sigma t, which means that the convergence is going to depend only on sigma, which is the real part of S, which means that your regions of convergences will never have a limit in the y direction. They will always have a limit in the x direction, because the y is j omega axis. The x is the real part of S axis, which is sigma. Now, a few pointers before I get started with the properties of region of convergence. I will walk you guys through the properties, and we will actually use them in problems. I'm not going to spend time doing the proof for the properties, just because it just takes time and it's turned out not to be too useful. But from previous semesters, I have the proofs recorded. The math is laid out in front of you. So if you look at it, you follow along the math, that's fine. If you want the recorded versions, ask me and I'll show you the links where you can actually look at the lecture for the proofs. But for this particular class, I'm not going to spend time proving the properties. I'll state them, and then we'll move on. We'll try to apply them for problems. So property number 1, what is that? In general, ROC, region of convergence, is going to be vertical strips in the S-plane. It is either going to be, this is my vertical axis, to the right of the vertical axis, to the left of the vertical axis, or maybe shifted to the right of this particular line, vertical line, to the left of this particular vertical line, and so on. It is never going to have a bound in the y direction. It is always going to have a bound in the x direction, on the x-axis. So you will see vertical lines that will bound your, or unbound, right? Like it may be to the right of the vertical axis, all of it, like there's no bound on the right. But it'll always be based on the real part of S. So vertical strips, because ROC depends only on sigma. And we looked at this example. Laplace transform of u of t, 1 over S, ROC was sigma greater than 0. Over here we saw that it shouldn't be in the pole should not be in the ROC, but if you look at the vertical axis, ROC will be to the right of that. Meaning there is no limit on the j omega, there is only limit on the sigma for ROCs. Property number 2, the region of convergence should not contain any poles of the rational Laplace transform. What are you doing here? We are just representing the Laplace transform of a signal, f of s, as a rational function, some polynomial in the numerator, some polynomial in the denominator. And we can do this to do what? To identify where the zeros and the poles are for that system. And if you have that, the region of convergence cannot contain any poles, because those are the points in S-plane where the function is going to infinity, right? It's not converging, so it should not be in the region of convergence. Now let's talk about the support, because I'm going to tie the region of convergence properties to the right-sidedness or the left-sidedness of the signal in time domain. I need to tie them. For example, I should be able to say, if the signal is right-sided, then the region of convergence is always going to be the right of the rightmost pole. Statements like that. So that the moment you sketch the signal in time, you know, oh yeah, region of convergence is going to be here. Done. All you need to know is what? The poles. Where are the poles? And you'll be done. Now, so to identify, to state the left-sided and the right-sided nature, we need to define support. What is the support? Support is the values of time for which x of t is not equal to 0. Those are called the support of the signal. For example, u of t has a support t greater than 0, t greater than or equal to 0. U of t minus u of t minus 1, that's a gate function, has a support of 0 and 1. Right? Below 0, it is 0. Above 1, it is a 0. Only between 0 and 1, it is non-zero. Right? So the value of t for which x of t is non-zero is called your support. For example, between 0 and 1, or greater than or equal to 0 here. So that's a support. Using support, we can define right-sided and left-sided signals. This is going to be probably the easiest part of the lecture today. A signal is right-sided if its support is bounded from the left by some arbitrary time t0. When you look at a signal here, this is u of t plus 1. Does it have a support on the left? Well, yeah. It has a support of -1 on the left. Right? There's no support on the right, infinity. So that would be called a right-sided signal. And you don't even need to compute the support for this. You can just look at it and say, all right, where is it moving? It is moving right. It is a right-sided signal. Doesn't matter where it starts. It can start here or it can start here. You look at where is it moving, right? Is it moving here? Yes. Is it moving here? Yes. That would be a right-sided signal. Example, e to the minus t u of t, right? Another example, cosine t multiplied by u of t, right? Moving right. U of t plus 1, another example. This one is u of t sine t. For all values that are over here, what is the support here? What is the t0 value here? What is the support on the left? 0, because that guy is 0, right? So you look at the signal, you know whether it's a right-sided signal or not. Why are we talking about this? Because later we are going to identify that the region of convergence for such signals is always going to be the right of the rightmost pole. Very easy, right? Like rolls off your tongue, right of the rightmost pole. And then we can also flip it around and say left of the leftmost pole. For what? Left-sided signals. The signal is left-sided if its support is bounded from the right. So in this case, I have a bounded support on the right. And even if you sketch this, you will also get the same thing. Do you guys agree that this is going to be a left-sided signal? You have a cosine t, and then you have a u of minus t. So you have flipped the u of t signal, and each value is getting scaled by a cosine function. So it's going to be moving left. And again, the finite bound here is, again, 0 here, right? But for this guy, it's going to be a 1. Where are you moving? Are you moving left or not? Yes, you are, then it's left-sided. So it has to be bounded from the right by some finite value t0. Questions about how do you identify left-sided and right-sided signals? All right. Signal is finite duration if it has both of them. Bound on the right, bound on the left, finite ones, t1 and t2. For example, here, u of t minus 3. It has a finite bound of 0 on the left, finite bound of 3 on the right, right? It's bounded. So that's a finite duration signal. So you've talked about right-sided, left-sided, finite duration. Is there a fourth alternative here? No bound. So what should we call that? Two-sided. Right-sided, left-sided. If a signal is both right-sided and left-sided, then it is two-sided, right? And if it is two-sided and bounded, then you call it finite duration. Something like e to the minus absolute of t. Going here, it was two-sided, right? Essentially, no bounds, right? No finite bounds on either side. Okay. So essentially, when I'll do this. I will say I've got a right-sided signal here I've got a left-sided signal here. I've got two-sided signal here. And I've got a, let's see, finite duration signal here. What does this guy look like? It looks like this, something like that. What does this guy look like? It looks like this. What does this guy look like? It looks like both. And this guy is just that, right? What about the region of convergence for these guys? ROCs. We'll prove this later, but I just want to connect the two right now. For a right-sided signal, ROC is going to be right of the rightmost pole, left of the leftmost pole. What is this guy going to be? Two-sided? Vertical strip, right? Vertical strip. And for finite duration? All of S plane. All right. So these there are four statements, right? So these will correspond to four properties. And as I said, I'll state them. The math is presented. I will not do the math. The math is essentially based on two things. I'll just tell you what is all the math is based on two things. One is, in order for things to converge, I need a damping exponential. I need something to go down with time. That's one thing. The other thing that all the proofs will rely on is, if you have area, right? So when you're computing, say, area of a signal, and the entire signal is above 0, it's all positive. Can I say that the area will only increase? If you have a signal that's always above 0, and I'm finding the area of the signal, right? I'm accumulating area. I can only increase, right? I can never go down. I can only increase. All the proofs are based on those two things. But if you're not able to follow the math and are interested in understanding more about the math, as I said, it's recorded. It's very easy for me to point you to the link, and you can play it at 2x speed and get through the math. But why are we not doing it now? Because I don't think that's too helpful in too useful expenditure for our time that is left. Let's move on. Property 3. A signal which is square or absolutely integrable has finite duration, with a finite duration, has ROC of the entire S plane. Like we said, if the signal is finite duration, then the ROC will have the entire plane. That's your property. That's your proof. And we are looking at sigma less than 0, looking at sigma greater than 0. Both will tend to converge. So the proof is there. Next, property 4. If x of t is right-sided, and we know how a right-sided signal looks like, and there is a line sigma equals real part of s, which is sigma 0, which is in the ROC, then there is any other line sigma 1 with sigma 1 which is greater than sigma 0 is also in the ROC. Very complicated way of saying something pretty simple. Let me just show you what that means. Say I have an S plane here. Let's pick two poles, right? Well, let's just pick one pole. Say I have a pole here, right? And it's a right-sided signal. So if it's a right-sided signal, this property is essentially saying the ROC is going to be right-sided. So what is that going to be? Well, I'll just draw an imaginary vertical line over there, and then I will shade everything over here, right? Now I'm going to pick two more lines. What is that? First I'll pick, say, with pink. Yeah, this is fine. And I will call this guy what? Sigma equals some, well, sigma 0, right? So real part of S is sigma 0 here. The equation of that line is the real part of S equals sigma 0. This is sigma. This is j omega, right? I've got a pole here. My region of convergence is here. I have picked some arbitrary vertical line in my region of convergence. Now, if I can pick another line, sigma 1, to the right of this, right? So for example, here, here. This is real part of S equals sigma 1. Because sigma 1 is greater than sigma 0 was in ROC, sigma 1 also has to be in ROC. That's a way of saying it's a right-sided, right of the pole, right? You guys see that? So if sigma 0 is in the ROC, then any other line with sigma greater than sigma 0 will also be in the ROC. All of this to say, if you have a right-sided signal, then your region of convergence will be to the right of the rightmost pole. Proof over here, as I said, I'm not going to go deep into that. What about left-sided signals? Well, if you have a left-sided signal, for example, over here, u of minus t, then you can, let's try to borrow the factor of e to the minus sigma t and look at the two options over there, e to the minus sigma t with sigma greater than 0, less than 0. So if sigma is greater than 0, you have something like this. Area exploding as time goes on. Over here, area converging as time goes on. So when sigma is less than 0, you're good. Sigma greater than 0, you're not good. You're growing with time. So when you have that left-sided signal, you see sigma less than 0 is good news. So sigma less than 0 points to a left of the vertical axis, right? So this is saying if you have a left-sided signal, then the region of convergence will be to the left of the leftmost pole. In this case, you only have one pole, so left of the pole. At any point, if you guys have any sort of reason to stop, you got to pull the chain and stop the train. Oh, that rhymed. Okay, what is the Laplace transform of u of minus t? Function is the Laplace domain. Put your signal in your Laplace transform integral e to the minus t dt. U of minus t is defined from negative infinity to 0, so I only got that. What is it? Value is 1, e to the minus t. Integrate, find the expression to be negative 1 over s. This will give you a pole at s equals 0. So for u of minus t, you have got a pole at origin. The Laplace transform is negative 1 over s. And based on this discussion, you can see that when sigma is less than 0, it will converge, which means the ROC will be to the left of the pole. Again, there will be no bond at the j omega. J omega doesn't contribute to the convergence. Again, pole should not be included in the ROC. Let's move on here. Next property. If x of t is left-sided, oh, okay. So same statement that is a little bit convoluted, all to say if your signal is left-sided, then ROC will be to the left of the leftmost pole. Signal is left-sided, then ROC is to the left of leftmost pole. Similar proof as before. Let's see. Here you have got a two-sided signal, e to the minus absolute of t. We did this example in the previous class. We found its function in the Laplace domain. We broke it up into two signals. One is right-sided, one is left-sided. We found out their individual Laplace transforms along with their individual regions of convergences. Then by using linearity property, we found the intersection of the region of convergences to look at it as a vertical strip. So if you have a two-sided signal, then you have a vertical strip as your region of convergence, which leads us to our property 6. Property 6 says if the signal is two-sided, then there will exist an ROC which consists of a vertical strip in the which is in a vertical strip in the S-plane. So right-sided it was extending right, left-sided was extending left. Two-sided signal, it is a vertical plane, vertical strip. Next, property 7 says x of s is rational, ROC is bounded by poles or extends to infinity. So either it's going to be bounded by the poles, like for a two-sided signal, or it's going to extend to infinity, as in the case of right-sided, left-sided, finite duration signals. Let's see. All right, these statements I've made again. X of s is rational, then x of t is right-sided, ROC is to the right of the rightmost pole, left of the leftmost pole. All right, I've looked at all these statements earlier as well. Right, so property 8 actually has more information than the previous properties, because it's focusing on many poles in the system. Then you have right of the rightmost pole for a right-sided signal. So in order to come up with the ROC, you only need to classify the signal as one of the four: right, left, two-sided, finite duration. Let's take a look at this example here and tell me what are the possible regions of convergences. You have how many poles? 2 poles, -1 and -2. Right. So I've over here put 3 different S-planes just to sketch the possible ROCs. How many are going to be possible? Well, I've sketched 3 graphs, so 3 are possible. -2 and -1 are your 2 poles. What are the 3 possibilities? Left-sided signal, all right, over here. All right, next. Strip. Next, right-sided. Right, those are the 3 possibilities. For each of them, let's try to identify what that is going to correspond to. Here, let me, all right. Here you have got ROC as what? Real part of S is less than -2, right? For which one it will be true for? Like what will this be true for? A blank signal. This is f of t, x of t. Come on. If you had a left-sided signal, that's what it would correspond to, right? Next, ROC is now bounded. In the middle, I can say what? -2 less than real part of S less than -1. And I can say this is V x of t is two-sided. Next, real part of S greater than -1, x of t is right-sided. It's a bit cold. My fingers are not doing the best job with the handwriting, so apologies for that. All right, questions about this example? Looking at just the pole locations, identifying possible ROCs, and for each of those possibilities, you're commenting about what type of signals would they correspond to. All right, let's do another example here. We are trying to find out inverse Laplace transform of x of s. We are given this, right? We are given that x of s is this, exactly the same as before, right? It has 2 poles, one at -1 and -2, and we know that the Laplace transform of any signal is identified by 2 things. One is this, and the other is region of convergence. And we are given the region of convergence. Real part of s is greater than -1. All right, real part of s is greater than -1. Right here, right? So you know that whatever answer you get has to be right-sided, right? Now, in order to get right-sided, what needs to happen for individual signals, right? There would be, for corresponding to this particular pole, there would be an inverse Laplace transform, and it would have its own region of convergence. Based on this pole, it would have its own Laplace transform and a region of convergence. The intersection of those two regions of convergences has to be this. So in order for that to be possible, what do the individual look like? They both have to be right-sided, right? So the ROC corresponds to this guy has to be right-sided. ROC corresponds to this has to be right-sided, so that the intersection satisfies this criteria, right? So let's just do that. So x of s, try to use partial fractions, and you guys are experts at that, I believe, right? Almost. Sure. 2 years ago, partial fractions. All right, later in the lecture, we are going to provide you with all the possibilities, and you will be like, all right, give me a partial fraction. Let me see if I can handle it. So the mantra is going to be bring it for partial fractions now. X of s, using partial fraction expansion, which we'll have cases for details later. Break this up into two. I've got 1 over s plus 1, and I've got negative minus 1 over s plus 2, right? So I've got s plus 2 here, minus 1 plus s plus 1 here. For each of these signals, I can find inverse Laplace transform, right? I'm trying to find the inverse of this, and I know the inverse of this. I know the function in the time domain. What is that? It's going to be e to the minus 2t u of t. And here e to the minus t u of t. That's pretty easy. But I could have picked the other left-sided signal as well, but I didn't. Why? Because I wanted the later signal to have the intersection such a way that it is right-sided. The only way it is possible if both signals are right-sided. So because both signals need to be right-sided, I will pick the inverse as e to the minus 2t u of t, inverse of this as e to the minus t u of t. Both of them, real part of s greater than negative 2, real part of s greater than negative 1. What am I not picking here? Let me try to observe this. 1 divided by s plus 1. I picked e to the minus t u of t. What else could I have picked? I could have picked this, right? E to the minus t u of minus t. That was a left-sided signal. I didn't pick that because I wanted my signal to be right-sided. You guys see how this works? All right. So I've got this from the first one. I've got this from the second one. Both of them right-sided. So I just combine them and write the time domain function as this: e to the minus 2t minus e to the minus t times u of t. Questions about this example? Given a function in the Laplace domain and its region of convergence, finding the inverse Laplace transform. Little game with partial fraction expansion, little game with identifying the type of the signal by looking at the region of convergence of the overall one. Very simple. Move on. Let's try to get to that partial fraction expansion, the identities. How do you break it up? So for that, we are going to need to express a Laplace transform as a rational function. So let's assume that the Laplace transform f of s, you can write that as a ratio of polynomials. And I believe when you were doing circuits, you must have done this, right? Writing it as a polynomial is in the numerator, polynomial in s in the denominator. The values of s that make the polynomial, the numerator go to 0 are the zeros of the system, and then the values of s for which the denominator goes to 0 is the poles of the system. So you've got p of s as your numerator. The roots of p of s will be called zeros. Q of s is your denominator polynomial for which the roots of q of s are called the poles. And you can mess around with the zeros or the poles to say do a filter design, right? And you know, as you were breaking up in the last class, that there was a discussion in here. So suppose you have sigma over here, say j omega over here, right? Let us suppose that I wanted to design a filter. Let's suppose I had a band pass filter, right? So if I had a band pass filter, I would try to do this, right? So as I'm going up and down on the j omega axis, what am I doing? I'm increasing and decreasing the frequency, right? It's just j omega. So it's sort of the frequency response of my filter. At lower frequencies, I'm trying to for band pass. So lower frequencies, I want 0 suppressed. At some band frequencies, I want higher, right? So wherever I want to suppress it, I'll sort of put my poles over there, right? And wherever I want it, I'll put my zeros over there. Wherever I want it to increase, I'll sort of put my poles there. And then I can bring it back to zeros. And then I can do the same thing over here. So you see, if you collapse this vertical axis and make it horizontal, you have low, then high, then low, high, low. You've got a bandpass filter there. You see that? The more number of zeros you put, the better it's going to be to make it down. The more poles you put, so as you increase the number of poles and zeros, the sharpness of that filter will keep increasing. Right? So you can sort of relate this to your filter design in circuits. And very conveniently, I have put my poles in the left half of the S-plane. You guys see that? Why did I do that? Stability. All right, you guys know like next two lectures now. I put my poles on the left side because that is a stable system. If my poles move to the right half of the S-plane, that's an unstable system. That's why I put them in the left. Let's come back. More about that later. So we'll talk about the math that supports that argument maybe in the next class. Okay, so we've got a polynomial in S in the numerator, denominator, zeros and poles and whatnot. Okay, how do we find inverse Laplace of this? No matter what function you have, you will face the problem of breaking it up into the partial fractions. Why? Because I have the standard form for 1 over S plus A. I don't have it for 1 over S plus A multiplied by 1 over S plus B. I don't have that. So I'm going to need to do partial fractions to decompose the function f of S into smaller fractions for which I have the standard inverse pairs that are in my table. So partial fractions, I'm going to deal with them over here. Let's learn about that. This is for general cases. We'll talk about 3 or 4 cases. F of S is defined as P of S divided by Q of S, polynomial in the numerator and denominator respectively. I have a polynomial in S of the order M. M is the highest power of S in the numerator. And then in the denominator, I have a order N polynomial in S. Now it's called a proper fraction if M is less than N, right? The numerator polynomial has to be less for it to be called a proper one. And if it's improper, then M is equal to or greater than N. And you can sort of go from an improper fraction to a proper fraction. How? Just do a division, right? So just do a long division. You may not need to go, very far, because all you need to go for is M less than N. The moment you get there, you can stop. The improper fraction can be expressed as some polynomial, and when you do that, you will get some polynomial function plus a proper fraction. So you can translate an improper fraction into some polynomial function for which I will know the inverse Laplace, and then you will be left with the proper fraction, which you will need to decompose using partial fraction expansion, PFE. Now let us say that Q of S is fully factored. The polynomial in the denominator is fully factored, which will essentially give us our poles of the system. We have the following cases that we will consider for partial fraction expansions for only proper functions here. We'll only do this for proper functions. If it is improper, then you have got to do a little bit of division and then come up with the polynomial function here. Separate it out. All right, case 1, Q of S has distinct linear factors. So if Q of S, that's your denominator polynomial, I'm factoring it out. So I've got S minus lambda 1, S minus lambda 2, and so on up to S minus lambda n. N is what? The order of my polynomial. It has to be greater than the order M, proper. And n is my distinct roots. They are all separate. They are all distinct, which means that they are not overlapping. Repeated, you don't have this as repeated roots. Then what do you have? P of S divided by Q of S in general can be written as k1 divided by s minus 1, k2 divided by s minus lambda 2, and so on up to kn divided by s minus lambda n. Distinct roots, factored, what else? Proper, right? Those are the requirements for this to happen. Now, how do you find k1, k2, kn? Well, you just find the residue, right? So you multiply the, you guys remember residue? Okay, so you multiply this function with s minus lambda 1, s minus lambda 2, and s minus lambda 3. Substitute s equals lambda I for getting ki. Let's try to actually play out that thing that is in general, but let's do it for a simple example here. Is this a proper function? Yeah, numerator order is 1, denominator is 2, so it's already a proper function. So I should be able to write it as two fractions, k1, oh, too big, k1 divided by s minus 1 plus k2 divided by s minus 2, right? Next, I need to find k1 and k2. So how am I going to find k1? Well, I can find k1 by putting a 1 for s, blocking off s minus 1. So I'm going to block off s minus 1, and I'm going to substitute a 1 here and here. What do you get? 3 times 1 divided negative 3, right? Yeah. Next, for k2, what do I do for k2? Well, I'll block off this guy, essentially like multiplying with that, right? So it'll cancel out. And then 2. I need to put a 2 in here and here. So I've got 6. That's it. That's it. Yeah. All right. Let me. Okay. Now, once you have this, after that it is your standard minus 3 times u of e to the minus t, u of t, do all of those things. Look at the standard tables, apply linearity, and then you will also need ROC. Here, I just worked with the function in S. I didn't have ROC. You would need ROC to be actually getting your complete inverse Laplace transform. You guys agree with that? I need the ROC here because I need to know whether it's right-sided, left-sided, and all those things. Okay, next, case 2. Q of S has complex conjugate roots. So I have P of S divided by Q of S. My numerator, and they're both proper. In this case, I have numerator written as AS plus B divided by S minus R multiplied by S minus R complex conjugate. So in this case, I have complex conjugate roots. So these cases are building on top of each other, right? So earlier you had distinct roots. Now you are adding a case where you have complex conjugate roots. So in some root that is S minus A plus JB and S minus A minus JB. Good. Oh, I absolutely don't mind you taking whatever approach. So with partial fraction expansion, when you guys learn it, I'm sure you have your own little, forms to deal with this. I'm absolutely okay with that. I hope that everything is going to be consistent. So yeah, if you are able to use other properties, go for it. This is one way to deal with it. Let's see. What is going to be for F? S. Well, this you can break down into C divided by S minus R, C conjugate divided by S minus R conjugate. All you need to find is C. How can you find C? Multiply this guy with S minus R and evaluate it for when S is R. Right? So if you look at case 1, you see this is for n distinct ones, right? In the middle, you may have 2 of them. You have the S minus R, and you also have S minus R conjugate. For that specific one, you have to deal with it as these 2 guys, where you are trying to find C. So again, you are trying to find the residue where you are substituting S equals R here, right? But you are not including this guy in there. So that's how you find C. Then you put it over here. C conjugate, you put it here. So case 2 is, how do you deal when the roots are complex conjugate? And if you have more than these one pair of complex conjugate roots, you do that so many times. Questions? Next, Q of S has repeated roots. So here what do you have? You have P divided by Q, polynomial in numerator, polynomial in denominator. You're defining that as P of S, leave it as is. Q of S has repeated roots, right? So you may have R of them as repeated. So you have R poles, all of them at alpha. And you have N unrepeated roots. How do you deal with this? Well, if you have N unrepeated roots and alpha repeats R times, so you have R repeated roots. For the unrepeated roots, you are already okay. That is exactly the same as before, right? All of them go separate ways. But when you have this S minus alpha raised to R, so R repeated roots, you deal with them this way. You have all the powers of alpha. You will need S minus alpha all the way to S minus alpha raised to R. And you've seen this, yeah, like usually you see it for a square, right? S minus alpha squared. You have S minus alpha, then you have S minus alpha squared as well. Both of the terms will be there. But their A's are computed slightly differently. For K's, it's going to be the same, right? Just as you did before. Just hide that particular factor, substitute the S equal lambda I for that Ki, and evaluate, just as we did before here. We got -3 and 6 here, exactly that same way. So that's how you would deal with these. But for A's, it's slightly different. For A0, you would multiply f of s with s minus alpha raised to r, and then evaluate that when s is alpha. So this is, you're multiplying with s minus alpha raised to r. That and that cancels out. All the others, you will substitute s equals alpha and get this, A0. You see that? Next, A1, differentiate this. What is this? F of s, multiply with s minus alpha raised to r, so that cancels out. S equals alpha, you already know that, right? You just got it for A0. Differentiate that once with respect to s, you get A1. Differentiate that with respect to s twice and divide by 2, you get A2. In general, you differentiate for a sub m, right? Any coefficient here for the repeated roots. Differentiate with respect to s m times and divide by m factorial. So you don't need to prove this, just identities, you can use it. Next, inverse transform with repeated roots for Q of s. So we are going to need to do partial fractions where it has repeated roots for the denominator. So differentiation property is going to help with that. When you multiply the signal in time domain by t, what you're doing in the Laplace domain is differentiating the function in s with respect to s, and you are also multiplying with the negative sign. You have seen this before, right? When we talked about derivatives. And that would apply for real part of s greater than lambda. The Laplace transform of e to the minus lambda t u of t is what? 1 over s minus lambda. This is, maybe I should write it here. That makes more sense. E to the lambda t u of t is your function. Its Laplace transform is 1 over s minus lambda when the region of convergence is r of real part of s greater than lambda. It's a right-sided signal. Pole is at lambda. When you multiply the signal with t, what do? You differentiate in s by multiply by negative sign. So you differentiate this guy and you multiply by a negative sign. When you differentiate this guy by with respect to s, you get 1 divided by s minus lambda squared, and there will be 2 negatives that will cancel out. So the inverse Laplace transform of 1 over s minus lambda squared repeated roots for Q of S is t e to the lambda t u of t. What happened? You just multiplied by an additional t here. ROC doesn't change. Real part of S is still greater than lambda. Why doesn't ROC change? Right, but it's also right-sided, right? So you can look at it and you can comment about the ROC here. All right. Now, if you differentiate once, you got a t in there, you can carry it out multiple times, right? So inverse Laplace transform of 1 over s minus lambda was e to the lambda t u of t. When you went for square, you got t e to the lambda u of t. When you go for cubed, you get 1/2 t squared e to the lambda t u of t. And you keep going for more factors. The inverse Laplace transform of a function which has L roots in the denominator, L repeated roots in the denominator, is going to be 1 over L minus 1 factorial t raised to L minus 1 e raised to lambda t u of t. Again, you can sort of prove these things. All you would have to do is keep differentiating the signal, right? Differentiate here. Whatever is left over, you will bring here, right? And over here you will be left with 1. Over here you will be left with half. Over here you will be left with 1 divided by L minus 1 factorial. So you'll bring it onto the left side, and you get that. Questions here, dealing with repeated roots. So, the procedure, I hope, is very straightforward. You give me a function in S. I will try to represent it as a proper fraction. Once I represent it as a proper fraction, I will use one of those 3 cases, or maybe I'll have more, other cases that I know. But I'll use my partial fraction expansion techniques to break it up, decompose it into separate x of s's, so that for each of them I can find the inverse Laplace transform, right? And based on the type of the signal it is, I'll define my region of convergence, or I should say the inverse. Depending on the region of convergence, I'll define my time domain signal, because I'm starting with x of s and I'm ending with x of t. Questions here? All right. I'm going to stop recording here because that is all I had prepared. Yeah.